Welcome to This Explainer. Okay, so if you work anywhere near manufacturing, tech, or supply chain logistics, you've definitely heard the term Industry 4.0 thrown around. It's this massive, sweeping concept that promises to completely revolutionize how we produce goods by blending physical machinery with advanced digital networks. But here's the thing. Despite being a huge priority for companies and governments all over the world, for the longest time, nobody could actually agree on what it meant. It had basically just become a blurry buzzword. And if you've ever felt a little lost in all the jargon, you are absolutely not alone. Get this. A production site manager at the automotive giant Audi actually admitted, even though Industry 4.0 is one of the most frequently discussed topics these days, I could not explain to my son what it really means. How validating is that? When top experts at leading manufacturings are struggling to define the core idea, you know there's a serious gap. That's exactly why we're using a foundational academic paper today to cut right through the noise. This explainer is going to be your concrete guide to what Industry 4.0 actually is, and more importantly, how to practically implement it. So here's our quick agenda for today. 1. The Industry 4.0 problem. 2. Crunching the data. 3. 4 core design principles. 4. A real-world case study. And finally, 5. The roadmap to smart factories. But really quick, how does this all build on history? I mean, the 4.0 implies there were 3 previous versions, right? The first industrial revolution brought us mechanical production way back in the 18th century. The second kicked off in the 1870s with electrification and the division of labor. The third, starting around the 1970s, was the digital revolution, bringing computers and electronics to the factory floor. And that brings us to today, Industry 4.0. It's a massive paradigm shift from centrally controlled processes to decentralized, completely autonomous production using the Internet of Things, or IoT.
All right, let's jump right into Section 1, the Industry 4.0 problem and crunching the data.
Since there was no universally accepted definition out there, a group of researchers decided they were just going to build one from the ground up. They didn't just guess, though. They systematically analyzed exactly 130 publications. And what's really crucial here is they didn't just look at academic papers. They looked at practical, industry-focused publications, too. They wanted a definition that actually bridged the gap between academic theory and real, boots-on-the-ground industrial practice. To find a real definition, they used quantitative text analysis. Essentially, they extracted single words as well as 2- and 3-word phrases from all those publications. They tossed out the generic stop words and grouped words by their stems. So words like autonomous, autonomously, and autonomy all got bundled into one single concept. By stripping away all that marketing fluff, they found the core functional terminology being used by the people actually building these systems. After crunching all those numbers, they shifted to a qualitative review. They looked at the context of the words and clustered them into 9 distinct design elements. But let's be real, 9 overlapping elements is still a bit too clunky for a practical framework. So they brought in 9 industry experts, folks from chemical companies and automotive manufacturers, for a structured workshop to refine those clusters into something truly actionable. Which leads us to Section 2, 4 core design principles. That expert workshop successfully boiled everything down to 4 core pillars. These 4 design principles are basically the mandatory requirements for any organization aiming to build a true smart factory. Honestly, if an initiative doesn't hit these marks, it's just not Industry 4.0. Let's break down each principle to see exactly how they work. The first principle is interconnection. This is the absolute foundation of the whole thing. It means machines, devices, sensors, and the people operating them are continuously communicating. They do this over the Internet of Things, which ultimately forms an Internet of Everything. Wireless communication is obviously key here for ubiquitous access, but it also requires modular standards, so machines from completely different vendors can just plug in and talk to each other. And of course, the researchers highly emphasize that with all this interconnection, robust cybersecurity becomes literally non-negotiable. Once everything is connected, you unlock this second principle, information transparency. This isn't just about having a ton of raw data. It's about fusing the physical and virtual worlds. Raw sensor data from the factory floor is aggregated and linked with virtual simulation models to create a digital twin of the actual plant. This gives you context-aware data. For example, the system doesn't just know a machine is vibrating. It knows exactly why it's vibrating in the context of the production schedule, and it shares that real-time info with everyone in the network. So what do you do with all that transparent data? That brings us to Principle 3, decentralized decisions.
The researchers identified this as the single most disruptive element of Industry 4.0. Instead of a central computer or a human manager calling all the shots, cyber-physical systems, or CPS, monitor and control the physical world autonomously. They make their own localized choices based on local sensor data and global network data to maximize productivity. They only escalate things to human operators when there is an exception, an interference, or conflicting goals.
Which naturally leads to the big question, what happens to the humans? That's answered by the fourth principle, technical assistance. Humans are absolutely not removed from the equation. Their roles are just elevated. The human shifts from being a mere machine operator to a strategic problem solver. And they get massive technical assistance to pull this off. We're talking visual assistance via smartphones, tablets, and wearables that aggregate data so workers can make highly informed decisions. It also means physical assistance from collaborative robots, cobots, that safely work side by side with humans, taking over the heavy lifting or tasks that are unpleasant or unsafe.
Okay, moving on to Section 3, a real-world case study. Let's look at how this actually plays out. A major chemical company actually partnered with universities to implement these exact principles, following a structured 5-step project roadmap. Crucially, step 1 was just creating a common understanding of Industry 4.0. They actually sat their team down and used those 4 design principles we just covered to make sure everyone was speaking the exact same language before they spent a single dime on new tech. Using that framework, the project team reviewed their existing logistics and production processes. They managed to identify 20 potential smart scenarios where Industry 4.0 could drastically improve operations. And we're talking a wide range of ideas here, from autonomously flying drones acting as inventory assistants, all the way to intelligent cargo containers that continuously monitor their own internal environment. But obviously, a business can't tackle 20 massive projects all at once. They needed a rigorous way to evaluate them. This is where the practical magic of the framework really shines. They used an analytic hierarchy process to grade the scenarios. They didn't just look at whether it made economic sense. They specifically scored each scenario on how well it complied with the 4 design principles: interconnection, information transparency, decentralized decisions, and technical assistance. Let's dive into the scenario that won the highest score, an assistance system for transport control. The contrast here is just staggering. The old way was incredibly analog. When goods were ready to move, an employee manually picked up a phone, called a central dispatcher, and that dispatcher manually assigned a specific human-driven vehicle to go pick it up. The Industry 4.0 way? A multi-agent autonomous bidding system. Here's how that actually works in practice. Both automated guided vehicles and human drivers carrying industrial smartphones act as agents in a decentralized network. When a transport order is generated, the vehicles literally bid against each other for the job. If a vehicle is far away or low on battery, it places a high-priced bid. If it's empty and right next door, it bids low. The vehicle with the lowest bid automatically wins the job. The result is this completely self-regulating, decentralized factory floor that requires zero central planning effort, leaving the humans to step in only when strategic help is actually needed. And finally, Section 4, the roadmap to smart factories. As the researchers noted at the end of their study, quoting another expert, Industry 4.0 is a phenomenon that will come inevitably, whether we want it or not. The transition to cyber-physical systems and the Internet of Things is already well underway. If you don't adopt interconnection, information transparency, decentralized decisions, and technical assistance, your competitors absolutely will. So I want to leave you with this provocative thought. How will your organization adapt to this inevitable shift towards cyber-physical systems and the Internet of Things? Are you going to be stuck making manual phone calls to a central dispatcher, or will you use these 4 design principles to build a self-optimizing, decentralized smart factory of your own? The framework is there. The next step is totally up to you. Thanks for joining me on this explainer, and keep learning.